Let's move on to a different and interesting subject, that is counting trees. So why would we want to count trees? Well, unless you're very interested in forestry, here is one example. So this example is known as Cayley's problem, and it comes from chemistry. So let's look at the setup of the problem. We want to count alkanes. So what are alkanes? They are molecules consisting of carbon atoms and hydrogen atoms. As you might remember from school, each carbon atom binds 4 other atoms, and each hydrogen atom binds one other atom. So for example, if you have 2 carbon, then you will, in order to fill up the empty 3 spaces of each carbon atom, you add hydrogen atoms. So this is C2H6, known as ethane. Another way, maybe let's take another example, that you have 3, and then you have the hydrogen atoms, and the carbon atom in the middle only needs 2 hydrogen atoms because it's already binding to other atoms. So this is C3H8. And so, as you can see from this drawing, that you attach 2 hydrogen atoms to each carbon atom plus 2 hydrogen atoms at the end. The general formula is CnH2n plus 2, as you might remember from chemistry. If not, just accept this as a fact or take my previous explanation. So, okay, but what about these? Why are they interesting? Well, starting from n equals 4, you can arrange the carbon atoms in more than one way. So if you have 4 carbon atoms, they can be arranged in a chain like that. Now I'm just going to draw empty lines because I don't have the energy to draw all the edges. But you know, there is only one way they can sit. They fill up these other spaces. And the other way is that they can sit like that in some sort of branching. So then this carbon atom only will have 1 hydrogen attached to it, but the others will have 3, so the total number is still 2n plus 2. These are 2 different forms of C4H10, butane. So why is this interesting? This is not just a game for mathematicians. Chemically, these 2 molecules have different chemical properties. So they are different molecules. It makes sense to look at them in different way. And since different arrangements imply different chemical properties, one question we might want to ask is, okay, so how many are there? For 4, you saw that there are 2. But as you can imagine, with these large alkanes, that, by the way, is an interesting topic to study in chemistry, they come in many different ways. So you can imagine that you can combine lots of carbon atoms in lots of different ways. And we want to know how many different kinds. So chemists want to do that, and what do they do when they want to do that? They turn to mathematicians. So we need to answer this question. So our job is to count these CnH2n plus 2 molecules. But of course, as a graph theorist, I know nothing about molecules, so let's reformulate this to a mathematical or a graph theoretic formulation. And as you will see, this will help us extract the essence of the problem and come closer to a solution. So what is really an alkane? Well, an alkane is a graph. It's connected because it's one molecule sitting together. It has n carbon atoms. Well, but what is a carbon atom really? In this sense, we only care about the fact that the carbon atom has degree 4. Chemists would say that it binds to 4 other atoms. This is one way to view the degree. And then we have the hydrogen atoms. They are 2n plus 2 in number, and they have degree 1. They bind to 1 atom each. So we want to count the number of such graphs. Now that we have the graph theoretic formulation, we can start doing some math. So first we make a few observations. So first we count the number of vertices and edges. This is maybe an intuitive thing to do in a graph. So we have n blue vertices and 2n plus 2 red vertices, so we have 3n plus 2 vertices in total. The sum of all degrees is 4 times n, because we have n vertices of degree 4, and then we have 2n plus 2 vertices of degree 1, so that's 1 times 2n plus 2. If you add up, you get 6n plus 2. And then from the handshake lemma, when we proved it, we said that the degree sum is twice the number of edges. It's always an even number, as you can see here. So the number of edges is you get by dividing this by 2. So you get 3n plus 1 edges. But now comes the fun part, because the number of vertices was 3n plus 2. And by this fortunate circumstance, the number of edges is 3n plus 1. So we have a connected graph, and the number of edges is 1 less than the number of vertices. And now you know this means our graph is a tree. So what we want to do, now we simplify the problem. We don't have to worry about cycles and stuff, because you know that all such graphs are trees. So we want to count all kinds of trees that arise in this fashion. The second observation is that there is no reason to include the hydrogen atoms, because for each arrangement of carbon atoms, the hydrogen atoms will automatically fill up the space so that we get the full molecule. So if we had, in the case of n equals 4, I showed you that we had this arrangement of carbon atoms, and we have this arrangement of carbon atoms. And in each arrangement, my hydrogen atoms would fill up the space as needed to give my carbon atoms degree 4. So I don't have to think about them. Their placement is uniquely determined by the placement of the carbon atoms. So we have simplified the problem to the following problem: count the trees that consist of carbon atoms. Well, a biologist would say all trees consist of carbon atoms, but let's go back to our problem. So how many trees on n vertices are there up to isomorphism? So what does this mean? Well, let's look at a few small n. So for n equals 1, there is only this one tree. For n equals 2, the only connected graph with 2 vertices and no cycles is this one. For n equals 3, well, you might have more than one, but they will all be isomorphic. So I mean, you might draw it like this, or you might draw it like this, but they are all isomorphic. So you also have 1 here. Here you had 1, here you had 1. For n equals 4, we had the 2. For n equals 5, in fact, we have 3. So we have this one. We have this one, which is isomorphic to the one where this extra line goes here. It's just, you are just mirroring them. So they are isomorphic. And you have the one with all the 5 in line. So there are 3. And you can check that for n equals 6, there are 6. So what is a general formula? Well, it's hard to get a general formula. So this is a hard problem. And as you know, in mathematics, when you have a problem that you cannot solve, there is an easier problem that you cannot solve. So you should solve that one first to get some insight, and then maybe later you can go back to your original problem. So the easier, maybe, problem is how many labeled trees on n vertices are there. So what is the difference between the problems? Well, now we don't care about up to isomorphism, so we have removed this condition and we are labeling our vertices. So let's look at a few numbers. So for n equals 1, we still only have this 1 tree. For n equals 2, we still only have this 1 tree. For n equals 3, I have this tree. I have this tree. And I have this tree. So these are 3 different trees. They are all isomorphic, obviously, but now I view them as labeled trees, and so now it matters if the missing edge is between 1, 3, 2, 3, and so on. So this will give me many more trees, but they will be easier to count. Another way to ask this question, instead of asking how many labeled trees on n vertices are there, you can ask how many spanning trees does Kn have. So again, for K3, the picture would look something like this. I get a spanning tree by removing any of the edges. So for K3, I have 3 spanning trees. And for n equals 4, you can check that the answer is 16. So as an exercise, construct all 16 labeled trees on 4 vertices to check that you are grasping the concept. So how many are there for general n? This was proved by Arthur Cayley in 1889, and he proved that there are n to the power n minus 2 different labeled trees on n vertices. Cayley was an interesting figure and proved many things in mathematics. He couldn't get a job after he graduated, so in order to get a job on the side, he studied law, and while being a lawyer, he proved lots of theorems, and then he became a full-time mathematician. I don't know at which stage of his career he proved this theorem, but that's not important. The important thing is that this holds. It's a very elegant and beautiful and short number to express. And it's a number that grows very quickly with n. It grows, both the exponent and the base grow. So as you can see, it gets huge already for a small number of vertices. This is a typical problem in combinatorics, that even with a small number of combinations, you have a huge number of possibilities. And this might give you a hint as to why the problem of determining these trees up to isomorphism is difficult. Because now for n equals 7, then from 16,000 something trees, you need to figure out which ones are isomorphic. And this is, if you do it brute force, this is a very large problem. In the coming lecture, we will prove this theorem in 2 ways, because there are many ways to prove this theorem that are interesting in themselves. But for now, I will leave you with this, that the number of distinct labeled trees on n vertices is n to the power of n minus 2.